So we're going to look at another application of the determinant, and this is for solving systems of equations, and there is several techniques to do this. One's called Cramer's rule, and this is one of the most, this is in my personal world, this has been one of the most used ways I've done this. The beauty of Cramer's rule is it allows us, you're going to see in a minute, allows us to solve for only one variable. So if we only need to know like x and we could care less about y or z, Cramer's rule lets us cleanly, neatly do that. Okay? And instead of giving you a formula, I found it better in my little world to know how it works instead of memorizing, here's how you solve for x, here's how you solve for y, z. So let's take a look at this. So I'm going to start with the system of equations. Now I'm going to do this with 3 equations. So 3 variables, 3 unknowns, 3 equations. And that's because, you know, just two systems, an x and a y or whatever, you can do those pretty readily by hand, using substitution or elimination, or even graphing for some of the more straightforward ones. When we get to 3, 4, 5, and beyond, it gets a little more challenging. So I want to start with the equations. Okay? So 2x plus y plus z equals 3. Now, of course, this is a manufactured problem to make the work a little straightforward for me, but this works for all systems of equations. Well, actually it doesn't. This doesn't always work for all of them. We'll talk about that one later. So x minus y minus z equals 0, x plus 2y plus z equals 0. Now, there's 2 things going on up here. We're going to take this and put it in matrix form. The first one's going to called the coefficient matrix. And the second one is called the answer matrix. Okay? The coefficient matrix is what it sounds like. The values before your variable, these are your coefficients. So I'm going to write the coefficient matrix. 2, 1, 1, 1, negative 1, 2, 1, negative 1, 1. And over here, I'm going to write the answer matrix. 3, 0, 0. Okay? From these 2 matrices, we're going to go ahead and figure out how to solve for x or y or z. Now notice this first column is x, then y, then z. That's going to be pretty handy in a minute. So here's how it works. Using your answer matrix, or your answer column, right? It's just a column vector. You substitute this with what you want to solve. So if you want to solve for z, you would take this guy here and put it here, and then we do some determinants. We'll see that in a minute. Or if you want to solve for x, you would take this, put it for the x column. And we're going to do that. So x is going to be the determinant, and I'm going to call it, we're just going to call it x, okay? And you're going to see y in a minute. And that is going to be divided by the determinant of just this matrix, D. Okay? We'll call this matrix D for whatever, okay? So we're going to take this guy here, we're going to substitute it for x right there. Let's go ahead and put that up there. So it's going to be 3, 0, 0. So, oops, wrong way. 3, 0, 0, 1, that is going to be divided by the coefficient matrix. 2, 1, 1. Okay. Again, I'm solving for x, so the x column is the answer matrix. Now, if we just had two equations, I would have a 2 by 2, and this would be a 2 by 1, and I would do the same idea. I would substitute these guys for these guys, or these guys for these guys. Same, absolute same technique, just less numbers, actually easier, but I choose something a little harder, okay? So, again, I'm gonna write these two guys over here. So 3, 1, 0, negative 1, 0, 2. And just so you see it, I'm going to solve the determinant up here. And down here, I'm going to do the same thing. 2, 1, 1, negative 1, 1, 2. Okay? Now we're going to do the determinant. So determinant is the diagonals minus the other diagonals. So the product of the diagonals. So 3 times negative 1 times 1. Okay. Plus 1, negative 1, 0. Plus 1, 0, 2. Okay. 3, negative 1, 1, 1, negative 1, 0, 1, 0, 2. Okay. That's going to be that minus the other direction, 0 plus negative 6 plus 0. Up here, this is negative 3 plus 6 equals 3. So my numerator is 3. So for the upper part, this numerator is 3. We're going to do the same thing down here. Okay, so 2 times negative 1, so negative 2 times 1, so negative 2 plus 1, negative 1, plus negative 1, plus 1, 1 plus 2. Okay. So 1, negative 1, 1 plus negative 1 plus 1, 1, 2. Let's see, 1, negative 1, 1, 1, 1, 2 plus 2. Oh, where'd I go? 2, negative 1, 2, negative 2, negative 1. Sorry, I messed up here. Let's try this again. So 2 times negative 1 times 1 is negative 2 plus 1 times negative 1 times 1 plus 1, 1 plus 2. Okay, that minus negative 1 minus 4 plus 1. Okay, these guys, those guys will cancel right here. I get negative 1. Those guys cancel. Add those up. You get plus 4. Okay, so now This is my denominator. So when everything's said and done, I get 3 over 3, which is 1. Okay, so I got this 3 up here. I got this 3 down here. And 3 over 3 is 1. So x equals 1. Okay? You can go ahead and do this. Give you the answers. Let's see. X equals 1. Y equals 2. Oh, negative 2. Z equals 3. Okay. I encourage you to go through the next couple. Again, coefficient matrix, the answer matrix, or answer column, answer, I won't call it, answer vector. Substitute for what you want to solve. So if you want to solve for x, you take these guys, put it into x. You want to solve for y, and z. Then the answer is going to be, so for example, for x, it's the determinant of what would have been the coefficient matrix, but we substituted the column in, divided by the determinant of the coefficient matrix. Okay. Now, when we started off, I said, this always works. No, it doesn't. Okay, here's when it doesn't work. What if we ended up with this? So we got a denominator, a numerator of 3. What if this out here equaled 0? No good. You can't have division by 0. So that means it's telling us something. It means it's undefined. But what it really means is there's no unique solutions, or no unique solutions. Okay, that's what this means, no unique solution. So if the denominator is 0, what you need to do is use another method. So if your denominator is 0, you're going to have to use another method to calculate the values. Okay. No unique solution would be situations where the lines overlap, where you have like a star pattern or like an H pattern. I think we talked about those last time. So, recap, Cramer's rule. It's by far strength of matrices and determinants. I did a 3x3. You can do more. You'll have to figure out how to do determinants for larger matrices. And again, it's the coefficient matrix, but you substitute whatever you're looking for. So this is the answer vector, this is the remainder part of the coefficient matrix, and this is the coefficient matrix. Take the determinant, divide it out, that is x. You can do it for y and z also.